I was a pretty successful young particle physics operative when I was a kind of a late teenager. And so, I had the...
Wait, you're doing particle physics as a teenager?
Yeah, I wrote my first paper when I was 15.
15?
Yeah.
So what age were you in graduate school?
I got my PhD when I was 20.
Oh, so you finished at 20?
Yeah.
Wow. Hey everyone, thanks for joining us. Today's conversation, a little bit different from some of the things that we've been focusing upon of late. We're going to talk about computation, the computational universe, a different way, really, of approaching science, which may provide insights that the traditional methods are unable to reach. And for that conversation, I suspect many of you have already guessed who our guest will be. That is Stephen Wolfram, founder and CEO of Wolfram Research, creator of Mathematica, Wolfram Alpha, the Wolfram language, and I should say from a more personal perspective, someone whose contributions have really radically changed the way we theoretical physicists do our calculations. So it really has had a profound impact. So welcome, Stephen. It's so good to have you again, part of our conversation. So I just wanted to jump right in. And so your career, and correct me if I'm wrong, but your career has kind of been a blend of fundamental science and then creating this wondrous, marvelous technology, the software that really has changed the way we do our calculations and really even approach calculations. So do you see these as two separate threads that every so often you go from one to the other, or are they kind of part of a coherent approach to try to understand how the world works?
At first they seem to be just sort of separate things, but increasingly I realized how coherent they actually are. So in nominal terms, I started out when I was a kid doing particle physics and using computers, and I've kind of done about 5 iterations of going between really concentrating on doing basic science, really concentrating on doing technology development. What's happened is the basic science has kind of shown me a bunch of conceptual things that have allowed me to do the technology development. The technology development has provided me with tools that allow me to do the basic science. And it's turned out that kind of the way of thinking about things that's relevant in doing the technology is surprisingly similar to the way of thinking about things that's relevant for basic science. I think, to me, it's sort of, in the end, most of these things are about sort of foundational thinking about things. Whether those foundations are what's really underneath biological evolution or machine learning or physics, or whether that's what are really the primitives that we should be building in this technology system. The other thing, which is perhaps surprise, is that, I make a living running a tech company. And that might seem like a very different kind of activity from doing basic science. But actually, it's more similar than one might think, because it's really, as far as I'm concerned, it's all about sort of the strategy of what you should do. And for me, kind of, I spend my time making lots of decisions about technology and so on. And it's a very useful thing to know sort of how to make strategic decisions. Then when one's doing science, it's like, okay, do we push this direction? Do we push that direction? It's surprisingly similar. And to me, it's very sort of invigorating to see that same kind of thinking play out on both both basic science and in technology development. And again, the sort of this thing that, for example, when it comes to sort of fundamental physics, I had thought, I was kind of developing a different way of thinking about how the universe is sort of computational all the way down. And I just realized, long after the fact, that some ideas that I developed for technology development having to do with transformations for symbolic expressions, which is sort of the foundation of a lot of our technology, that is embarrassingly similar to the foundational kinds of things that I think about for physics, even though I imagined that they were coming from two completely different sort of lines of thought. Actually, the most bizarre thing is that back in the early 80s, when I was doing a bunch of technology development, trying to understand things about recursive function evaluation for technology development, I thought I was doing that. I was also working on gauge theory and QCD and quantum field theory and so on. I thought and also in general relativity and so on. I thought these were completely separate activities. only to discover recently that the questions about sort of how you choose simultaneity surfaces and so on were actually kind of the same story in both cases. So, 40-something years ago, I thought I was working on two completely unrelated things. And now, about a year ago, I realized it's actually the same foundational problem.
So I'd love to get into some of the details there, but I do have a follow-up question, and I really do mean this in the most positive light. I'm just wondering, do you ever worry or consider the possibility that because you have been looking at the world from a computational standpoint through all the technology that you have been developing, that you have this powerful hammer that you've developed, and in some sense, you're looking for other nails that it might be able to, hammer into. So could it be that it's really your mindset that is creating the synergies as opposed to there being some objective connection between these things?
Well, look, as a practical matter, I talked about strategy for doing things. I like to find nails that hammers that I have can actually do something with. So yes, there is some part of that. But another thing to say about kind of the computational way of thinking about physics and the world is if we lived in a different time, I probably wouldn't use the word computation to describe what we're doing. It's really a question of you have definite rules, you're applying these rules, you're seeing what their consequences are. In modern times, for most people, computers are the quintessential example of that. In another age, it might have been, I don't know, telling, army troops what to do or something, follow these rules and make this, tortoise configuration or something. It's just computation is the metaphor that is the useful one today for thinking about sort of understanding systems by just seeing what consequences do these rules have when you apply them over and over again.
Now, famously, you've shown over the years how very simple rules that allow you to update a system, say a cellular automata, can take you from a very simple initial condition and simple rules to very complex output, complex behaviors. As a flat-footed physicist, I wonder about the following. I mean, I can always consider the laws of physics to be a rule that takes the universe at time t and evolves it forward to time t plus epsilon. And of course, people actually put the laws of QCD, for instance, the laws that you mentioned, lattice QCD is a system where we don't exactly do it, but you can always imagine doing a version of what I just described, and people do that. And so in what sense would that not be a version of what you're describing?
Okay, well, so first point is you said T plus epsilon. Right there, you kind of lost me because, as soon as you're saying something like time is a continuous thing where you can pick any possible value of time, that's not something where you're kind of just following discrete rules. So that right there, you have to bring in all the apparatus of continuous mathematics, which kind of blows you out of a lot of the phenomena that are the most important ones that we learn from computation. In other words, to be able to apply those methods from continuous mathematics, you simply can't have a lot of the structure that is going on in these computational systems. That's one thing to say. The other thing to say is a lot of phenomena that I've understood by doing computational experiments, thinking about their results and so on, those phenomena absolutely existed in simulations people had done for other purposes, but they ignored them. In other words, there's a rich literature of places where people had kind of studied systems similar to ones I've studied, and the main thing they said was, there's some kind of noise in the system, and it's kind of a nuisance, and we don't really care about it. And what they concentrated on was the things where there was enough regularity that they could have a simple narrative that they could tell about what was happening. And that's and that narrative is typically a narrative that's based on mathematical methods, and it's sort of things that can be reached by using mathematics, so to speak. And so the big surprise, which surprised me a lot, was, when you just do computer experiments, and you just see how the chips fall, you see kind of what actually happens, there's this big surprise that even though the rules you put in may be very simple, the thing you get out is very complicated. Is such a phenomenon going on in simulations and lattice QCD? I'm sure it is. Has anybody looked at that? Probably not. even though I've been telling people to do that for decades. I mean, I also would say that we've made a lot of progress actually recently in understanding quantum field theory in the context of our physics project. One of the hacks of lattice QCD is time isn't really time there. You have to make this kind of, this sort of time is like space. There isn't and I think we can finally fix that. And that makes some of these phenomena a bit easier to understand. But yes, I think the question is, for example, let's take lattice QCD as an example. The big question in QCD remains, how come quarks seem like they're permanently confined inside things like protons? We've never seen a free quark. How does that happen? Well, there's a certain amount that's known about that, but what's really going on there? We really need to know things about, what the configuration of the QCD fields really is. What are they really like? Probably they're really complicated, but that's not what people measure. What people do is to measure some particular, number that represents some, correlation between this and that or something of this kind. My guess is if you really want to understand what's going on, you have to do things like look at what's the actual, very complicated configuration of fields. From doing that, you will get different intuition about how things work. But that hasn't been the traditional direction that's been gone in doing mathematical science, because mathematical science it's fantastic when it works, because you get to have some sort of, here's a formula. It's kind of we're done here because we have this formula that says what's going to happen. But that's kind of not, you're sort of ignoring a lot of the structure of what's going on. Now, when it comes, we talked about time a little bit. I think it's a place where one really sees this difference. In sort of the traditional mathematical physics approach, time is at some level just a parameter. You can say, I've solved this system. I've got this t parameter in my formula. I can pick any value I want for that t parameter. In the computational way of thinking about things, time is the result of sort of the continued application of rules. And there's no guarantee that you can just sort of jump ahead and say, oh, I know what the answer is going to be, a million steps, a billion steps. That in the sort of traditional mathematical approach, going a million steps and going a billion steps is just changing that t parameter. But in the kind of computational approach, it's really applying this rule more and more times. And there's this phenomenon that seems to happen quite a lot, which is this idea of computational irreducibility. You can't actually just figure out immediately how to jump ahead. You're forced to kind of live time as time actually progresses, kind of go through the steps one by one. I think that's a sort of important distinction between sort of the computational way of thinking about things and the mathematical one, where it's just like there's going to be a formula for the result.
And so that's such a vital idea, computational irreducibility. Again, just to reiterate what you said, when we solve a physics problem, we have the answer. Maybe it's a function of t, and we just choose whatever t we want, and we get the state of the system at that particular moment in time. That, as you're saying, in many systems, you can't do that. You have to actually go step by step by step. Can you prove a system's computationally irreducible? I mean, is that an airtight mathematical proof? Are there conditions that need to be satisfied where you can say that is definitely one of those problems where you can't have a t parameter and jump ahead?
This is a complicated story. So it really dates back to things like Gödel's theorem from 1931, which is kind of a version of this kind of statement. It's saying what one is saying is there are versions of the statement. For example, if you say, "Can I know what will happen after an infinite time in this system?" That's a sharper distinction than "Can I know what will happen? Can I know quickly what will happen after a million steps, a billion steps, whatever?" Basically, there are sort of ways one can poke at this question where one can say, yes, there is sort of undecidability. There is computational universality. There are these properties that all sort of point in towards computational irreducibility. Really, the bigger principle is this thing I call the principle of computational equivalence, and which is a kind of a guiding principle for a lot of what I think about and so on. And it's sort of an interesting, let's say what it is first. Basically, you have some system, it's got some definite rules. You can think about the progress of that system as being like the doing of a computation. then the question is, how sophisticated is that computation? Is that computation one that I could get some other system that's much simpler to do it, or is that computation kind of as sophisticated as it could be? And the principle of computational equivalence says when you get above things whose behavior is obviously simple, you will generically have computations that are as sophisticated as they could be. And so one of the consequences of that is computational irreducibility, because when you're trying to predict how a system is going to behave, it's like the system is doing its thing and computing what's going to happen, and you on the side are trying to say, I'm going to outrun that system. I'm going to be smarter than that system. I'm going to do my computation more efficiently than that system. Principle of computational equivalence says in general that's not going to be possible. So, but now, what is that principle? In other words, is that a statement? Is that something you could prove from the laws of physics? Is that a statement about defining the notion of computation? Is it about what kind of a statement is it? And it's a complicated mixture of those things, very similar to, and actually it's closely related to things like the second law of thermodynamics, which it's not clear what kind of a statement that is. Is it a statement about the sort of the laws of physics as they are? Is it a statement about the ways that we can prepare states and so on? But this is a long way of saying what we're seeing is this is sort of a guiding principle for thinking about things, and we keep on seeing it. It has predictions about what should happen. It says, in this particular class of systems, if you just enumerate those systems, as soon as you get past ones whose behavior is obviously simple, you should show the features of being as sophisticated computationally as anything can be, like, for example, computational universality. And so very nicely, one can check off in a bunch of these kinds of systems, yup, that theoretical prediction is satisfied. Took a lot of work to prove it, but yes, it's satisfied. And you can keep sort of poking in at different features of this kind of overall intellectual framework, and seems to keep on doing very well. But it is a conceptually complicated thing, because it is sort of all tied up with what you even mean by computation and so on. So it's not something where you can sort of say, we'll do an experiment and we'll just prove this principle, because it's a principle that is also related to the definition of things. But it's very nice that one can make sort of theoretical predictions and they keep on checking out. And that's very encouraging for sort of an intellectual framework.
Yeah. And so I want to turn to the physics project that you mentioned just a little bit ago. And just by way of introduction, most of our audience is, of course, familiar with the fact that the big discoveries, if you will, of the last 150 years, we physicists focus usually on 2 or 3 of them. We always mention quantum mechanics. We always mention the general theory of relativity. And sometimes we throw in statistical mechanics and so forth as another fundamental pillar of our understanding. And my understanding, again, which is rudimentary of some of the work that you've been doing recently, is that you have suggested that your approach can yield at least some of these key ideas from this computational standpoint. But before we get to that, I just want to ask the following question, which is related to what I asked before. Can you reverse engineer the systems that you build in the following sense? Can you start with the laws of the general theory of relativity, discretize them in some clever way, map them to a cellular automata in some clever way, have clever rules that approximate Einstein's equations? And so if I challenge you not to find the general theory of relativity, but rather to implement the general theory of relativity in your computational paradigm, is that always doable? Is it tough to do? Is it trivial to do?
Well, that would be the traditional kind of natural science approach, is drill down from what we already see.
Right.
That was the thing, you asked about sort of my own personal trajectory. That was the thing that I learned to do when I was doing things like particle physics and cosmology in the 1970s. The thing that for me was a very useful personal experience was in building tools, partly to do that, I kind of tried to, I built my first big computer language computer system. And in doing that, the way I approached doing that was a drilling down process. I was saying, want to do all these different kinds of computations. Let me drill down and find the sort of atomic primitives from which I can build that up, kind of traditional natural science thing. But then I had the experience of going from these primitives that in that particular case I just completely made up, and seeing sort of how one built from that into this whole structure that did lots of interesting things. And so that gave me the impetus a few years later to say, well, maybe I should try doing something like that for science, much later for physics, of just saying, let's look at all the possible rules we can imagine. Let's drill down to the simplest possible rules and just build up from there and see what happens. And the big surprise at first was you get all these kinds of complex phenomena that seem relevant to lots of kind of everyday features of physics and biology and so on. It took me another decade to kind of see how that might be related to kind of what was underneath space and time and things like that. But the reverse engineering approach is kind of, it's much harder work than the big surprise is that you can do this thing where you start from the simplest foundations and end up getting things that kind of relate to what we already know is true. And, it's not at all obvious that something like that would work. I mean, to give you an analogy, let's say that you were starting from laws of fluid mechanics and somebody said, I want you to figure out, how do you drill down from that? Well, it turns out you can get the laws of fluid mechanics by thinking about lots of discrete molecules bouncing around, but it would be pretty hard work, I think, to figure out from the laws of fluid mechanics that, you could actually represent that by a bunch of discrete molecules. You'd probably end up with some very complicated setup that wasn't actually, in that particular case, what we know is going on. So, the approach that I've taken is a much more extreme approach that, on its face has absolutely no reason to work, which is just start with the simplest things, build up from there, see what happens. The big surprise is that it does seem to work. So, in other words, and for example, when it comes to, the Einstein equations, for example, I've just been looking at this recently because I'm trying to get I'm chasing my kind of beliefs about what may be happening with space-time and dark matter and so on. And to do that, I actually have to have good, accurate reproductions of things that one can compute with the Einstein equations, starting from these very simple underlying rules. So I'm more acutely aware than I might be about all of the complications of both traditional things that people do in simulating the Einstein equations and what I have to do. And I think it's but in terms of how do you get to something where you're saying I can simulate this thing with the Einstein equations? The big surprise is just like with discrete molecules, and you look at lots of them, you get something that looks like fluid mechanics. What happens in this case is you start with this discrete underlying graph structure for space-time. You build up from that, and we can show mathematically at a physicist level of rigor that yes, the limit of those kinds of underlying processes is the Einstein equations. I say at a physicist level of rigor because, for example, in the case of even molecular dynamics giving fluid mechanics, for 100 years or so, people kind of gave up. But people were trying to sort of rigorously mathematically prove that limit actually works. That's never successfully been done. I think some things I've done recently kind of show one why that's hard and give one a pointer to how it might be done. But at sort of a physicist level of kind of this is how the limits work, we can show that underlying sort of rewriting of these hypergraphs and so on leads to Einstein equations. Then you have to say, okay, let's do it in practice. Let's actually simulate something that starts off as a couple of black holes, look at their merger and so on. Then you have an immense level of complexity, which has also afflicted people starting from the Einstein equations and trying to discretize them and get them on computers. And we have many of the same issues about, what's a valid, consistent initial condition, how exactly do you do the updates and so on. It is very encouraging that the things we're doing can get you. It's not difficult to get to something which is close to what one would get to in terms of the answers with sort of a discretization of the Einstein equations.
And so when you say you get to the Einstein equation, just so I sort of understand the target, because I want to drill down a little bit, can you, in other words, you do some work with your basic primitives, and out at the end of that is r mu nu minus a half g mu nu r equals 8 pi g over c to the fourth t mu nu. That's what pops.
Yep, that's the idea. And so let me explain what's sort of involved in that. So remember the derivation. If you think about the derivation of fluid mechanics from molecular dynamics, this is a very similar kind of thing. And you might say, oh gosh, we got the Navier-Stokes equations with all of their detail and so on. Turns out that detail is just sort of the mathematical physics representation of something that at some level is a much simpler story. And I think it's the same thing here. The fact that there's, the half R G mu nu, so to speak, is, that's sort of a detail of it has to be that way, given that we're making this thing that's traceless and
well, that's what I was asking. So for instance, are you imposing a certain kind of local energy conservation? Like what are you putting into the system? Right.
So it's surprisingly little. I mean, so what's, the underlying idea is that sort of space and everything in it is represented by this hypergraph. Just a thing where you have these atoms of space that are just sort of discrete points.
And those are just nodes in this hypergraph.
Yes, and all you're saying about them is how they're related to other nodes.
And the relation is whether they're touching each other by some link in your hypergraph.
Yeah, whether they're linked, whether they're connected, when you draw it as a graph.
Right.
And so then what you're doing, you're saying that's the structure of space. Time is something very different from space in these models. Time is the progressive rewriting of that hypergraph by using some rule that says whenever you have a little piece of hypergraph that looks like this, transform it into one that looks like that. And turns out, very similar to the case of fluid mechanics, it doesn't matter so much what that rule is like. Just like, air molecules, water molecules, they have very different kind of scattering processes, but when you look at them in the aggregate, they have the same laws of fluid mechanics. It's kind of the same thing here. There are some limitations on that, but that's roughly the idea. And then the question of how you get from that sort of microscopic thing, what happens when you kind of look at a large scale? You have to ask questions like, how do you get from this network to anything that is even vaguely like space? The first thing you have to answer is, well, what dimension of space? The network, you can connect things any way you want. It's a friend network. There's nothing that says that there's anything sort of three-dimensional about your friend network, and nor is there here. So what you can kind of define the dimension by looking at, start from one node,
sort of scale
how many nodes you get to, right? And you ask what the growth rate of that is. Now you start to see why something like the Einstein equations might be a relevant thing to show up, because if you say, well, look at the growth rate of this kind of ball of nodes as you go a certain graph distance out, you say the growth rate is like r to the d, where r is the distance you've gone and d is the dimension. Okay, so then you say, well, what would it look like if this thing wasn't just an approximation to flat space in d dimensions? What if it had some curvature? Well, turns out that the correction term, if you just look at this growth rate thing, the correction term is the Ritchie scalar curvature, which, interestingly is something that shows up in the Einstein equations. And it kind of, that's the beginning of things starting to kind of fall out, is that, so it comes from something that is very simplistic, just asking for growth rates of volumes in this hypergraph. And then you have to ask, well, how is that volume affected by these rewriting rules and so on? The other big thing you have to deal with is the right-hand side of the Einstein equations, the T mu nu, the energy momentum story. And so a big question in these models is, what is energy? And I had at first assumed that to know what energy is, I would have to know what particles are. And my qualitative picture for what particles are is they're kind of like sort of knots in the ether in some sense. They're kind of like they're things that are kind of like topological topological features of this network that sort of persist Because the big thing about particles is particles, like electrons and things, they can move from here to there, and it's still that same electron when you arrive, so to speak. So it's like, what is the thing that is sort of a robust feature of this structure? And that's kind of a topological object in this network. So I thought one was going to have to know what a particle's like, and then one was going to have to try to figure out, what's the energy of a particle like. But actually, there's a bulk definition of energy, and it's basically just the amount of activity in the network. So, in other words, when this network is you having all these little events where a piece of network is being rewritten into another piece of network, and well, to be a little bit fancier about it, you can build up a causal graph that represents the causal interdependence of those events. So if you have one event, it produces a bunch of atoms of space. Another event is going to come along and it's going to consume some atoms of space.
These are now the rules that you're putting in for the updating of the hypergraph.
Yes, that's right. So so then one has one event, it produced some atoms of space. If the next event that's coming along needs atoms of space that came from the first event, then you say there is a causal relationship between these events. These events have to be, in physics terms, time-like separated. It has to be the case that one of them has already happened by the time the next one happens. And so you build up this whole graph of causal relationships like that. It turns out that given that graph of causal relationships, you can say, well, I can trace what corresponds to sort of a time-like path in this network of causal relationships. If I want to know what is space like at a certain instant of time, then I'm going to make kind of a transversal to that. I'm going to make a space-like hypersurface in the language of relativity that is something that is in the language of, in the more mathematical language, you can say that there's a partially ordered set of these of these events, and this is a so-called anti-chain. It's a thing that goes across where every event that's in this kind of space-like hypersurface can be said to be happening simultaneously. And then there's another space-like hypersurface where those events are all time-like separated from the ones on the previous space-like hypersurface. Okay, so it turns out that energy in these models is the flux of causal edges through space-like hypersurfaces. So in other words, you've got the space-like hypersurface that represents the kind of instantaneous state of space, and you're asking, as we look at events that happened before that space-like hypersurface and after, we're saying that the kind of the flux of causal edges through that space-like hypersurface, that's our way of computing energy. And so momentum, for example, ends up being if you have a time-like hypersurface, it's just the flux of causal edges through time-like hypersurfaces. By the way, one of the nice things that comes out is when you kind of unravel all the stuff about space-like hypersurfaces and so on, you can understand why special relativity works in these models. But one of the things that's always been a bit mysterious, at least to me, about special relativity is that there are these transformations that link space and time in special relativity. There are also transformations that link energy and momentum in special relativity. The question is, why are they the same? That was something where, they just happen to be the same. I mean, mathematically, it's very nice that they're the same, but why are they the same? In these models, it is absolutely inevitable that they're the same. In other words, they have to, because of the way that one is defining energy and momentum, and what one is considering to be energy and momentum, the transformations have to work the same way as they do for space and time. That's just one
Sure.
side feature.
But can I there's some questions in there that perhaps you can illuminate me on, because where does the causal structure come from? Because just naively, we could live in a Newtonian universe in which there isn't a speed of light limit on the speed with which signals can, transmit from location to location. How does your model eliminate that logical possibility? Or is it simply that's another set of rules that do not yield the Einstein equation?
No, I don't think you could make a version of the models that we've been dealing with that have an infinite speed of light. I just don't think that would, because what's happening is, as soon as you have the idea that, space is this kind of discrete network of atoms of space. There is a sense in which there's and then you have the idea that you're updating that network using rules that sort of have finite information content. They're not rules that reach across the whole universe. They're rules that somehow involve only a finite amount of information about there's this network and it's a little piece of network, and whenever it looks like this, it gets transformed to one that looks like that. So as soon as you have that sort of finite information content of the rule, and you have the idea that things are made of this big graph of discrete structure, then you inevitably have that implies finite rate of information transmission. But it's the speed of light in our models is just a matter of units. I mean, in other words,
I understand.
There are these updates,
Yeah.
and if you say, well, what is the transformation between the time between these updates and sort of the distance in across the network that it can go, that constant of proportionality is the speed of light. It's just a feature of units. But so I think in a model like ours, infinite speed of light would require infinitely complex rules, which is, that we can't, you can't. It is a sort of fundamental fact about science that the universe doesn't seem to have infinitely complex rules. If the universe had infinitely complex rules, every different particle in the universe, so to speak, will be doing its own thing, and we wouldn't get to talk about laws of nature and kind of have a way to take nature and sort of crush it down to sort of a narrative that we can understand.
Right.
But so a fundamental fact about science is sort of there is some finiteness to the rules that are being applied. As soon as you have that idea in the context of these models, I think you inevitably have what will work out in physics as finite speed of light.
Right. And so the other sort of, when we teach the general theory of relativity, some of the things that we usually focus upon are the fundamental symmetries of space-time, ideas of general covariance. We like to emphasize at the get-go that your T parameter and your spatial parameters naturally are knitted together into a mathematical structure by which we can do the local Lorentz transformations that allow, So if your approach from the get-go singles out time as just the updating parameter, and space is quite different, it's built from this causal network, is there a tension there, or does it somehow all work out in the end?
I think there was a mistake made back in 1919 when Minkowski said, let's take space and time, and isn't it cool that we can make a quadratic form? Minkowski had been a number theorist studying things like that before. Isn't it cool that we can put space and time together in this mathematical structure that, says t squared minus x squared, more or less, and that looks like this nice mathematical thing? I don't think Einstein actually had that point of view.
He didn't like it at first, but he did warm to it.
Yes.
Yeah.
But I think I think it was a mistake. I think it's mathematically elegant, but I think it's as physically missing.
You mean a mistake for science to think that way? I mean, there was no error, obviously, in that formulation. Right. You're saying it's just the wrong direction.
It's a wrong direction because it packages together two things that are really, space and time in our common experience don't seem like the same kind of thing. You can kind of go to a lot of effort to make them kind of seem like the same kind of thing by, telling various relativity stories and so on. But the fact is, our common experience of space and time, they're somewhat different. And in our models, the fact that, t squared minus x squared and, Lorentz transformations and all that kind of thing show up is an emergent feature. It's something which is true only in, the limits of a large number of a large region of space and things like this. And for example, by the way, when it comes to speed of light being maximum speed of transmission of information, even that is only an emergent approximation. Because what happens is that basically what you realize is that if you could do infinitely good engineering, which you never can, then you could go faster than light in these models. So let me try to explain that. So there's sort of an analogy which happens when you think about gases and things like that with molecules. In the rooms that we're in, molecules are going, a micron before they hit another molecule. They don't go. It's not like a molecule that starts here immediately zips at the speed of sound to the other side of the room. They're going in this kind of random walk. But if we were able to kind of piggyback on a molecule, and if at every collision of those molecules we were able to figure out which molecule should we choose to piggyback on next, then we could go across the room at the speed of sound. We wouldn't be, just diffusing across the room like this random walk. Okay, so there's an analogous thing that happens in space-time in our models. So we have this structure of space that is this network, and we're saying, sorry, this is a little complicated, so it takes me a moment to think through how this works. What we're dealing with, we have this causal graph that represents all these different events that we can think of as being events in space-time, and each event has effects on subsequent events. So that there's kind of a cone of effects. So we start off from this one event, and we get a light cone's worth of other events that depend on that first event, that are causally affected by that first event. And so now the question is, so that light cone defines this whole collection of events that can be affected from the first event. And that in a sense, now we ask for sort of the projection of that light cone onto a particular sort of moment in space, a moment of time that gets a kind of on one of these space-like hypersurfaces. So now the question is whether, when we are looking at, if we're asking, how do we kind of, our definition of space is, we can think of it as being the result of kind of slicing this light cone. And the basic point here is, just like we can do with the molecules in the gas, so if we pick the exact right kind of causal edge to attach ourselves to, we can end up getting to a place in space that is further away than we should be able to get to, based on this kind of light cone of what the effects that can be defined are. So it's because of the relationship, because of the fact that space is just an emergent thing that is knitted together by all of these causal events, that we can kind of get through space faster than we should be able to. Now, in order to do that, we would have to kind of know exactly which update event we should select next to attach ourselves to. So there's two big problems with that. One is the computational irreducibility problem, that it's hard to know what's going to happen without actually having it happen. So you can't kind of outrun the universe and see where to go next. You just have to wait and see what the universe does. That's problem number one. Problem number two is, a critter like us, that's some kind of observer of the universe, certainly doesn't fit through kind of one or two atoms of space. In other words, nothing like us can be transported that way. Just like in the case of, molecules of air in a room, nothing like us is transportable on molecules of air. So it's kind of but it is an interesting thing that at some level, the problem of going faster than light is in some sense an engineering problem. It's not in some sense a feature. It's not something that's burnt into the structure of the model. It's a feature of what you can actually get done as for example, as an observer or experimentalist like us in a model like this.
Yeah, it's interesting. I don't know if you've been following much about some of the recent work emerging from holography in ideas of quantum gravity and string theory, but there has been a suggestion by a number of physicists that if you could undertake infinitely complex operations, that you'd be able to effectuate non-local properties, non-local interactions. So maybe there's some resonance.
I think it's very closely related.
Yeah,
I think that the whole, the whole holography story ends up playing out in an interesting way in our models. I mean, we don't, the I's are not dotted and T's are not crossed in this story, but roughly here's how it works. So, what we've been talking about is we have this hypergraph that represents the structure of space and everything in it, and we're talking about the updating of that hypergraph and how that in the aggregate produces kind of the laws of space-time. But one of the things that we're kind of a little bit sweeping under the rug in the first description is we say, well, there's this update. But there are actually many possible ways that updating could be done. All we've defined is whenever you see a piece of hypergraph that looks like this, rewrite it to one that looks like that. But actually, there are many different places where that rewriting could be done.
Is it like order dependent? Is that sort of like if,
yes.
Yeah, okay.
Yes.
Yeah.
So you get essentially many paths of history. So we get these things we call multi-way graphs, which represent the different possible sequences of updating events. And what can happen, people have talked about kind of many worlds approach to quantum mechanics, where one says, there are many different possible histories to quantum mechanics. That's what's happening here as well. But there's one big difference, which is made obvious by the fact that these models are discrete, which is that not only can you have branching, you can also have merging. In other words, it can be the case that you start off with two identical states of the universe. They end up in two different states, but those two different states can end up both evolving to the same state. If this was a continuous system, you would say that will never happen. The probability of the two things landing at exactly the same number is 0. But in these discrete models, it happens all the time. And so you get this complicated structure of branching and merging, essentially paths of history, branching and merging sort of threads of time going on. And the thing that is sort of the if you look across those different branching and merging threads of time, and you say, what's the structure? If you make a slice across this multi-way graph of threads of time, what is the structure that you get there? Well, you can say, well, these two threads of time are somehow nearby because they had a common ancestor. They had a recent common ancestor. These other threads are further apart. You can make a version of space that isn't like ordinary physical space that we're used to. It's just another kind of space that corresponds to the map of these different threads of history. And we call that branchial space, the kind of space of quantum branches. And it has its own geometry and so on. And branchial space is where kind of quantum mechanics plays itself out. So we think more or less that in quantum mechanics, one thinks about quantum amplitudes that have things like a complex number phases and so on. We think that those phases are roughly positioned in branchial space. In fact, my guess is that another mistake of packaging that was made about 100 years ago was to say that when we think about quantum amplitudes, that they have a magnitude and they have a phase as complex numbers, and that they're all sort of packaged together as a complex number. I think that's a mistake. I think the magnitude comes from a completely different place than the phase. The phase is kind of this position in branchial space. The magnitude has to do with counting the number of paths that you can follow to get to a particular point. But in any case, the basic idea is we've got this notion of branchial space, which is kind of a different kind of space than ordinary space. And one of the big sort of claims is that what in physical space is the Einstein equations is the path integral in branchial space. So in other words, the sort of one of the ways to think about the Einstein equations is that the presence of energy and momentum, say the Einstein equations, is deflecting sort of shortest paths in space-time. I mean, that's kind of the
usual story. Yeah,
that's the usual story. That's what you've taught for years and so on. And so, presence of energy and momentum deflects shortest paths. Okay, so in branchial space, the same kind of thing happens. So except that there, the question of what it means, okay, so presence of energy and momentum is deflecting paths, which is changing phases of things because it's sort of moving things around in branchial space. But now in the path integral formulation of quantum mechanics, one's talking, what that says is that the amplitude for some path depends on what one's changing the phase of this quantum amplitude based on the presence of relativistically invariant energy momentum, the action. And so what this is saying is that in what is sort of playing out in physical space as being something explained by the Einstein equations, in branchial space is what the path integral is saying. Which is already kind of cool.
I mean, it's very interesting, and there are two directions I'm struggling with which one I should go, and I can't resist doing a little bit of quantum, although I anticipated doing some more general relativity. I may double back. But if if this is an approach to generating now quantum mechanics from this underlying computational system, and if you're following sort of a path integral-like approach, do you have to put in like the weighting factor, e to the I action over h bar? I mean, where does that come from in your?
Oh no, it comes from the fact that it is part of the equation of motion in branch-Hill space.
But it emerges from?
Yes, it emerges in the same way that in general relativity, if you're simply computing. So remember, I was saying that energy is basically the density of activity in the network. And so what then happens is that if you ask what happens to a shortest path in the network if there is a certain amount of activity in the network, you can kind of get some idea. I mean, there's a bunch of sort of mathematical versions of this, but the rough qualitative picture is if stuff is happening in the network, then the shortest path from here to there is going to be affected by stuff happening in the network. And it's the same story in branch-Hill space for quantum mechanics, that the stuff happening in the network, and again, there's many footnotes to this, and it's a slightly, but the qualitative picture is stuff happening in the network deflects paths in branch-Hill space, and the deflection of paths is a change of phase. So what one's saying is the presence of energy momentum is changing the phase, which is essentially what the path integral says too.
And you're saying that emerges. None of this is being, in other words, I guess another way of saying it, and again, I wish I understood the innards of this more, and I'm appreciative of your patience for, describing this all to me. But if you had no understanding of the general theory of relativity, if you weren't a physicist at heart and didn't have the training of a physicist and hadn't worked in physics, and you had no understanding of the Schrodinger equation or the Feynman path integral, and you were just taking this computational approach, is it the case that you would have extracted general relativity and quantum mechanics from this approach?
I think I would have to be pretty good to be able to do that, but yes. I mean, just as if you what you start from computer simulations, you try and figure out what are the kind of the emergent laws. I've tried to do that in lots of places where people didn't know what the emergent laws were, and have had some success there. If you're asking me, would I have successfully been able to sort of extrapolate from what I'd seen in computer experiments to deduce those laws, I would say that will be a stretch for me. I don't think it's not conceptually impossible, but to have thought of the right things to study would have been challenging.
Well, you see, like the example I could give you, and this is perhaps a poor example, and maybe a self-serving example, I don't know. But when you study string theory, you study the quantum mechanical equations of motion of a string. And it really is the case, and you can say this with confidence and you're not hiding anything. If you didn't know the general theory of relativity, but you knew quantum mechanics well enough to study the quantum mechanical motion of a string, you could really extract out the Einstein equations from that knowledge, from that structure.
You know what? I would disagree with that. I mean, because they come out essentially as a consistency condition and so you wouldn't, the fact that there is such a consistency condition, you wouldn't have even thought to look for that. You just said the strings flap around and they have non-causal things happening and they have tachyonic modes and they have this and that and the other. So what, you might say? You have to know there are no faster than light modes and so on in the physical universe.
Yeah, I'm not saying that you can get it without putting any physical insight into the system. But what I am saying is you're putting in insight that does not require any knowledge of the general theory of relativity, the Einstein equations. That's a better way of saying it, the Einstein equations.
Yeah, at the same level, you would deduce the same thing here. I mean, this is, you would, it would be nice if you knew some differential geometry, because then you would think about, studying kind of these kinds of aggregated quantities. But I mean, those, for example, if you ask, have graph theorists, come up with these things sort of independently, they've gotten the kinds of quantities that you would think about looking at based on knowing general relativity are not quite the same, but they're not super far away from the kinds of quantities that people who just study graph theory have thought about looking at. So I think, in that sort of counterfactual history, so to speak, I think there is there's a decent chance. I wouldn't give myself 100% chance of noticing the right connections, but it's a I think it. I mean, again, I've had the good fortune, in a sense, to work in a bunch of areas where I start from the computer experiments and one doesn't know the emergent laws. And so, I've had to try and deduce those and see what their consequences are and so on. And I think, knowing from both sides is convenient, but I don't think that one was kind of fudging it to be able to meet somewhere in the middle. I think that's sort of an inevitable thing.
Now, there are, obviously, as you're very familiar with, puzzles in the general theory of relativity, such as the cosmological constant. So Einstein wrote down the Einstein field equations and famously did not include the cosmological constant at first. And then when he found that he gave rise to a dynamic universe that he didn't like, he put it in. And later on, he removed it when the observation showed there was a dynamic universe. And then fast forward 70 or 80 years later, we put it back in to account for the accelerated expansion. So since you're getting Einstein's equations, extracting it from this computational framework, do you have insight into the cosmological constant?
Maybe. I mean, this is what, the thing I'm currently trying to do of really tightening up sort of how we deal with general relativity in these models is an attempt to understand that better. The issue is, in traditional general relativity and quantum field theory, there's always been this mystery about, how can it be the case that there are all these vacuum fluctuations that are implied by quantum mechanics that have all this energy associated with them, and yet they don't seem to have a gravitational effect. They're not curling our universe up into a little ball because because of all that energy, so to speak. And that's been sort of a strange and mysterious thing. In our models, that issue doesn't really come up because it is those things that we can think of as quantum fluctuations. It is that microscopic structure of space-time that is, it's the activity that knits together the structure of space. So it is not the case that we have on the one side thinking about, quantum fluctuations and so on the other side thinking about the structure of space-time. In some sense, the quantum fluctuations make the space-time. So that means that means one isn't immediately thrust into the question of how come there isn't an immensely huge cosmological constant associated with kind of all of those vacuum fluctuations, but it kind of puts one on the hook to have to derive, well, what is the effective kind of, what is the zero, so to speak? Because there's a certain amount of activity that's necessary to knit together the structure of space. Then the things that we are looking at with, actual massive objects sitting in space and so on, those things are, above that zero. And figuring out where the zero is something one has a chance to actually be able to do. Now, my expectation is, so my current guess, which might be wrong, is, dark energy, which is less politely called negative mass matter, or negative mass stuff, is what is sort of associated with the zero kind of thing. Whether dark energy is a real thing, I'm not yet convinced experimentally, but that's a different issue. Then there's dark matter, which has been kind of known about in some signs of it have been known for 100 years, and my own guess is that, again, a bit of a mistake was made in calling it dark matter, because that implies that it must be something related to matter. And my analogy for this is what happened in the 1800s with the question of what heat is. People noticed that heat could flow from one substance to another. What flows? Well, it must be a fluid.
Caloric.
So they invented caloric fluid, yes. And of course, by the end of the 19th century, it became clear, well, that's not actually right. It's discrete molecules and so on. That's heat is the motion of discrete molecules. So my kind of, irony of scientific history is the thought that dark matter is really the space-time analog of heat. It's a macroscopic manifestation of the microscopic structure of space-time. Now, have I proved that? Absolutely, I have not. But that's
just wondering if that idea is correct. Would the equation of state of that thing that you just made reference to be the same as the equation of state, or at least in the appropriate limit, as that we use for dark matter? A pressureless.
Yeah, right. I mean, the fact that it's pressureless means it's kind of just a bit like space itself, so to speak. I mean, that might even be a clue right there. But I think that's obviously what one has to derive. I mean, the question is, if you were just presented with, here's a solid, and I'm telling you there are these discrete molecules that are running around inside it, what effect does that have? It would not be easy, I think, to deduce, laws about heat and so on. This is the situation that we have here. It's even a little bit more complicated because of the fact that it's not the idea of this network the structure of space and so on is a little bit less concrete than having this block of solid in front of you.
Right.
But kind of yes, this is the question is how does one get sort of accurate enough in one's going from this discrete underlying network to the continuum structure of space-time and so on to be able to say, is there some extra little effect that isn't quite the Einstein equations that gives you what we are thinking of as dark matter, so to speak?
Wait, so you're suggesting there's kind of a correction term to the Einstein
Yes.
equations when you go to the continuum limit. What is that? Do you have that? Do you know what that looks like?
I don't know what that's like. But I mean, it's worth remembering. And, if we go a little bit technical general relativity, there's the left-hand side of the Einstein equations is all about the structure of space-time. The right-hand side is all about energy momentum. When you think about gravitational waves or something, there's sort of a trade-off. You can say, well, I'm going to stick that on the right-hand side as part of the energy momentum story, or I can stick that on the space-time side. So if you're asking, in this case, you say, well, what's the correction term like? I suspect it'll be the same kind of thing. You could talk about the gravitational waves as being a correction term to the left-hand side if you wanted to, although that's not the way one usually thinks about it.
Right.
So, but if you're asking how does this work? I don't know yet. This is just a guess. I mean, this is a thing where, this idea that it's a feature of the structure of space rather than something associated with particles, one reason that's important or observable in a sense is if it's a feature of the structure of space, that's something that's happening at the scale of the elementary length, at the scale of kind of which might be, 10 to the minus 100 meters or something. It's really tiny. If one's talking about it being particles, one could say, well, people are doing, dark matter searches, and there's going to be one particle that comes through every minute, and it's a discrete thing. Whereas if it's a feature of the structure of space, it's like, well, there's this tiny effect, and there's a gazillion of them at every moment. So it's really a different kind of thing. You would never expect the one particle event that you would think of from dark matter in a kind of particle interpretation.
Now, another puzzle, in addition to dark matter, dark energy, are singularities. So, famously, the first closed-form solution to the Einstein's equation was not written down by Einstein, it was written down by Schwarzschild. And when you look at that solution, people often describe it as it sows the seeds of the own destruction of general relativity, because at the center of this solution, which we now call the black hole solution, there are things that become infinite, invariant things that can't be done away with by a coordinate transformation, curvature invariance and so forth. So you must encounter those in some form.
Yes.
And what do they look like in your language, and what do you do about them?
It's very interesting. I mean, so in a Schwarzschild black hole, for example, you can't represent everything about a Schwarzschild black hole using a continuum view of space. You kind of have to punch a hole out at the center. There's this sort of singularity where you say, well, the Einstein equations don't quite apply here. We're going to assume that space-time has a little hole in it. Well, in our models, it's nothing like that. That seems like a hack. You don't have any kind of thing like that hack in our models. First of all, in our models, things are discrete. So the idea that, for example, there is a transformation between one kind of topological structure of space-time and another that has to be sort of this strange discontinuous thing when you're dealing with traditional general relativity and manifolds and continuous structures, that it isn't a discontinuous thing in our models, because something that sort of didn't have a hole, there isn't a notion of a distinct whole, so to speak. It's just there's a structure of network, and when you look at the sort of emergent properties of that, you can describe it as having a whole. Now, in the case of the Schwarzschild black hole, the thing that happens is you can think about the singularity at the center of a Schwarzschild black hole as being a place where time stops. Every geodesic has finite length. If you're falling in there, after finite time, you're toast, so to speak, at the singularity. So in our models, what happens is that you get something where time literally does stop, because you are thinking about rewriting this hypergraph, and at some point you realize you've got a structure of hypergraph where there is no more rewrite that applies. So time corresponds to the progressive rewriting of this hypergraph.
And how do you see that? How do you see that there's no updating, there's no application of your rule? Like, what does it mean that, I know what that means. Yeah, go ahead.
Yeah, it just has a kind of discrete structure that is such that there just isn't a little, depending on what the rule is, there isn't a configuration of atoms of space that are related in this or that way. There just are no atoms of space related in that way in the place that corresponds to the singularity in the black hole. Now, in the case of our models, the event horizon of a black hole is very easy to recognize, because it's a place where there is the event horizon of a black hole is a one-way event horizon. Cosmological event horizon will be a two-way event horizon where you can get information in neither direction. But whatever it is, the question is, are these causal edges that are associated with this causal graph, do they both go into a region and out of the region, or do they only go into the region? And so you can identify a black hole as being a place where the causal edges only go in, information can get in, but nothing comes out. And so there are a lot of that's a fairly easy thing to identify. Now, when you ask about things like rotating black holes, where things get funkier in general relativity, what seems to happen is that at the critical rotation rate, isn't really rotation, but the critical rotation-like parameter, rate, if you were to exceed that, you would disconnect a piece of the universe. So in other words, what happens is that in our models, you end up with fewer and fewer causal edges that connect these different parts of space-time. And if you were to have a black hole where the J parameter was greater than M, it would disconnect.
And just so I understand, the nuts and bolts a little bit of this. So if I said to you, I'd like to see in your description, a black hole solution that has mass M, angular momentum J, maybe electric charge Q. Do you know how to set up your hypergraph, and then you have your fundamental rules at hand to see how that evolves through your updating through your temporal parameter?
I can't do the charge part. Electric charge, I don't know how that works yet. For mass and angular momentum, yes, we can do something there, but you got to understand we don't know how to make a black hole from nothing. That takes a lot of computation to get a black hole from nothing. So the best we can do, which is, by the way, the same thing you would do in relativity, is to say, let's start from that configuration. And so we can start from this continuum metric, for example, and we can say, let's say how we would make a hypergraph approximation to that metric. So we can set that up, and then we can say, okay, how would that evolve under our rules? Okay, and so that's the way in which you can say, well, what then happens? Do you get something which is a kind of a stable sort of solution to general relativity that way or not? It's a bit tricky, as it is in the case of numerical relativity. And the reason it's a bit tricky is, as I mentioned, in our case, it's a little bit more physical. Why it's tricky? Because there are these different possible updatings orders that you can use. And depending on which updating order you use, you may or may not end up with something where you're sort of evolving time in a reasonable way as opposed to an unreasonable way. In other words, if you said, I'm going to do all the updates here, I'm going to do kind of this, I'm going to update many, many times in this place, and I'm not going to update it all over here, you'll get funky things happening. And that's the exact same thing happens in numerical relativity. And so we have pretty much the same set of issues as numerical relativity. If you if you say, I'm going to pick updating rules, so what does it mean to pick these updating rules? Basically, it's saying, if you imagine an observer observing what's going on, the observer believes that certain things have happened and other things have not happened. It could be the case. There's no, and so So having an observer who has sort of a reasonable way of probing what's happening, you're going to end up with a reasonable sequence of updating events happening. And that will give you the same kind of thing that you see in numerical relativity. But and rather nicely, some of the issues you see in numerical relativity, like you say, well, in this particular place, there's high curvature, and so we have to put in more points in our numerical relativity. And we do that kind of by hand. In our models, it's not by hand at all. The reason there's more curvature is because there's more activity in the network, and that means there's more nodes in our hypergraph. In other words, we're sort of doing the analog of sort of an adaptive numerical method is happening because of the physics of what's going on, not because we chose to put it in from the outside, so to speak. But, this is, I will say that as far as I'm concerned, this is subtle stuff. I mean, it took a long time. It took until 10 years ago or something before people had decent numerical relativity for black holes. And that was, a solid, 100 years after, the original construction of general relativity. We're way ahead of that schedule. But it's still subtle stuff.
I mean, can you see gravitational waves in your?
Yes.
I mean, is that?
Yes, one can. I mean, now, and one can see, when one computes, you can compute, the Ricci curvature. One can compute, Weyl curvature, the form of curvature that lets you see gravitational waves and so on. It's that all works nicely.
And are there any? And this is maybe the wrong question. I don't mean this in to be provocative at all. But are there any insights that you can get from this approach that people who are doing more conventional numerical general relativity cannot get? And I know that the value of what you're talking about is you're going deeper to the atoms of space and time. But in the larger scale limit, are there insights that you can?
Yeah, I think so. I mean, the question is, what effects will you see here that you wouldn't see in traditional general relativity?
Right.
And, okay, so one of the more dramatic ones is dimension fluctuations. So in this model...
Oh, I see. Nothing guarantees an integral number of dimensions. Yeah.
Right. And that can fluctuate. And so we don't know how much it should fluctuate. We would really love to have an analog of the standard continuum, Friedman, Robertson, Walker metric for the early universe, a homogeneous universe, which in the traditional way of setting it up, you can have sort of the one parameter universe where you just say what the overall, curvature parameter, the overall sort of scale parameter is for the universe. We'd love to have a version of that sort of solution for a homogeneous universe that includes dimension as a dynamical parameter as well. We don't quite know how that works. We are somewhat handicapped by the fact that the apparatus of calculus and kind of things like differential geometry built over the last 300 years is all built based on the assumption that the dimensionality of space is an integer. So, and it's all, you do univariate calculus with one variable, you do it with multivariate with a few variables, you don't do 2.3 dimensional, 2.3 variable calculus.
Well, I think there's this thing called non-standard analysis where...
It doesn't help you.
That doesn't
help you. That's solving a different problem.
Okay.
This is I think it is fair to say, and we've been poking at this for long enough, that I think all of that there's really nothing known about this issue. I mean, like if you say, what's the Riemann tensor in 2.1 dimensions? One just doesn't know.
Right.
And so we've been trying to build what we call infrageometry, which is geometry where the underlying structure of space doesn't start from kind of space like Euclid said it was like, but starts from this hypergraph. And that's been a bunch of mathematical work, which we're getting further with. But we need to have that in order to really, sort of tighten up these discussions of how exactly things work. You need this kind of framework to think about.
Now, you described earlier on how you define dimensionality here, which makes perfect sense. You look at the causal relationships, you see how they scale with some notion of radius, and if it goes like r to the d and so forth. But do you find that your updating rules tend to preserve that dimensionality, or do they preserve it within an integer? So if it's at 3, it'll bounce around 3.2, or does it go up to 5 or something like that?
Well, sort of things come to equilibrium usually fairly quickly. for the same reasons that they do in gases. I mean, it's basically what happens is, and it's a symptom of computational irreducibility, that basically things evolve to sort of the average random place fairly quickly. And once they're in the average random place, things don't change much. Now, there certainly are rules which crush down to, 0 dimensions and things like this, and expand out to infinite dimensions and so on. We kind of, the other tricky thing is that it matters what the updating order is. In other words, you can have a pathological updating order which can make crazy things happen. But that pathological updating order isn't the one that observers like us, so to speak, would ever see happening in the universe. In other words,
it means something about us as observers that restricts the kinds of systems that we could ever encounter?
Yeah, I mean, it's one of there are two key things about us as observers which turn out to be crucial in the models that we have. One is that we're computationally bounded observers. So if we could follow every individual molecule, if we could follow every individual atom of space, we wouldn't even believe in continuum fluids, continuum space, because we just say, look, I can just see where all the molecules are going. I can see where all the atoms of space are going. For example, we wouldn't believe in the second law of thermodynamics.
Of course.
If we were not computationally bounded. The fact that, what's happening in the second law is we're going from this sort of maybe simple initial condition through this irreducible computation to something which we as computationally bounded observers just sort of throw up our hands and have to say it looks random to us, rather than, I can see how everything went. That's one assumption. The other assumption that turns out to be important is that we believe we are persistent in time. In other words, even though we might be made of different atoms of space at every successive moment in time, we feel that we have a continuous thread of experience through time. And it's important that we have a continuous thread of experience. It's actually important that we have a single thread of experience through time. That's the thing in understanding quantum mechanics and how we deduce things from quantum mechanics. It's important to understand that these different threads of history, we have to conflate those together, because we're going to say we think definite things happened. Whereas, in a sense, at the level of the universe underneath, many different threads of time are taking place. For the universe underneath, many different things are happening. For us, we're conflating those together. By the way, it's a sort of in space-time, the fact that we are pretty big compared to the elementary length, the distance, the sort of the structure of this network, and so on. We're big, so we just average a bunch of things out. Just like we do for fluids, for example. We say we're not looking at the individual molecules because we're pretty big compared to the molecules. In the case of quantum mechanics, it's a little bit more subtle because we're big. We span many different paths of history. So our minds effectively have the same branching and merging of paths of history going on in them, but we are taking a big sample out of branchial space. And that's kind of why we end up believing that definite things happen. Just as if it was the case that we were looking at sort of a fluid at the level of molecules, we wouldn't say, the fluid is going in this definite direction. We'd say, it's got all these different directions it's going because all these different molecules are going all these different ways. But yet, when we average it on a large scale, we say, the fluid is flowing in this direction. And it's the same kind of thing with what's happening in quantum mechanics. I mean, it's a tricky thing because, for example, you can ask, why is there randomness in quantum mechanics? Why is it not, in these models, everything is kind of determined. So at least at the level of this multi-way graph of all possible threads of history, the kind of the structure of all possible threads of history is completely determined. What is not determined is where we are as observers within that whole kind of within across branchial space and so on. Which branches did we actually sample? And the analogy that I think is perhaps useful is if you say, what does the night sky look like? You say, there are these stars in the night sky. Well, and we all agree about what it looks like because we're all on the same planet. If you say, what does the night sky look like according to the laws of physics? We can't say that because it is a contingent thing that depends on us being, in the particular place we are. But the important thing is we all agree about what it looks like. It's an objective reality for us because we all happen to be nearby in physical space. And I think the same thing happens in branchial space, which is why when we do some quantum experiment, people can agree, oh yeah, that was the answer for that quantum experiment. Not because that's the only possible answer there could be, but because in a sense, the minds of all those people are close together in branchial space. And so they all kind of perceive the same threads of history.
Right. So, Stephen, there's a whole basket of questions that I would like to ask at this point. Unfortunately, I know that we're running out of time. I mean, the questions
I can go a bit longer. You're asking. This is fun. We got to go a bit longer.
Well, if you're up for it, I mean, the questions that then come to mind for me, if we're going to talk a little bit about quantum mechanics, is in quantum mechanics, perhaps the strangest quality of the theory of all is entanglement. Schrödinger famously described it as not one, but the quality of quantum mechanics which distinguishes it from a classical worldview. The tricky thing about entanglement, of course, is if you're dealing with a computational system that's local, your updates, your rules are all local updates, as I understand it. So where, from your perspective, does this non-locality, this very modest kind of non-locality, but still quite wondrous, where does that emerge?
There are many threads of history. They don't have the same, the different things are happening on these different threads of history. And by the way, the sort of notion of entanglement is bizarrely direct in these models, because literally you're dealing with these different threads of history and they are entangled in the sense that they have common ancestry, so to speak. So these things that are happening on different threads of history are connected because they have the sort of common ancestors in this graph of possibilities, but they're not. There's nothing that says that they have to be the relationship between what is spatially distant and what is distant in branchial space. Those are two different things.
Sure.
Now those two things get knitted together in this thing we call the multi-way causal graph, where you have this notion of, you have two events, for example. You can say those events are time-like separated. One has to follow another in time. They can be space-like separated in the sense that they can both be at the same time, but you can think of them as different places in space. They can also be what we call branch-like separated, where they are occurring on different branches of history. So all three of those are possible. Now you can make this whole graph that shows the causal relationships between things in space, in branchial space, and through time. And so then that whole object is kind of the ultimate story of what are the relationships between all these events that can happen in the updating of this hypergraph. And so we were talking a little bit before about holography, which is sort of this connection between things that happen in general relativity and things that happen in quantum field theory. The way that works, I think, in our models is that this multi-way causal graph is this knitting together of things that are associated with space-like separation and things that are associated with branch-like separation. And in a rough approximation, quantum mechanics is one projection of this in essentially the branchial direction, and general relativity is another projection of this essentially in the spatial direction. And so that's kind of how that relationship works out. And some people have looked at the ER equals EPR, which is kind of a quintessential example of holography. And there are claims that you can see that phenomenon in our models. I'm not yet totally convinced myself, but that would be a nice thing to be able to, that's sort of this quintessential connection between the world of quantum mechanics and the world of general relativity. I
mean, do you see wormhole-like solutions presumably as well if you try to create them much like black hole solutions?
Yes. You see, I mean, my favorite of these things I call space tunnels, which are these things that have a different dimensional space. So that's a thing that's different from general relativity. It's a wilder collection of things that can happen than in general relativity, particularly because of this dimension change thing. Now, in terms of, you were asking what can we see that is different from what you see in general relativity? I would say, well, the number one effect which doesn't depend on the elementary length scale is dimension fluctuations, because that is a feature of models like this that we don't have to know kind of how big that elementary length is. I mean, Einstein was kind of lucky that some of his predictions didn't depend on the one parameter in his theory, namely the cosmological constant. I mean, things like the bending of light around the sun being a factor of 2 different than it would have been in the Newtonian theory. It's convenient that the 2 didn't have a lambda in it, so to speak. Although for me it's a major cautionary tale that, when the bending of light around the sun was first sort of computed, it wasn't, they didn't get the right answer.
Yeah.
And then the experiment was almost done at a time when they would have said it doesn't
World
agree.
War I got in the way, and that team was arrested as they crossed into Russia, as I recall the history of it. Had they not been arrested and measured the bending of starlight, they would have ruled out Einstein's first prediction of the bending of starlight.
Right. So this is for me, this is a cautionary tale in terms of, the theory is difficult to work out. The experiments are difficult to do. It's complicated to navigate, having the meet in the middle. But, so the next big class of things is the macroscopic effects of what one can call space-time heat. I don't know what they are yet.
So you like calculating things like how a particle's trajectory might be affected by fluctuating dimensions or scattering experiments? I mean, that's the kind of thing.
Right. That's the hope. I mean, the thing with dimension fluctuations is seeing really bizarre gravitational lensing, where, normally light is bent by the presence of mass in gravity, but a dimension fluctuation would produce some very bizarre kind of shattering of wavefronts of light, but it's complicated to work that out, and it also depends on exactly what the form of the dimension fluctuation is, which we don't really know. We just know that's an effect that you can get in models like this.
Right.
Now, I mean, there are other pieces. There are other kinds of things one can. You talked about particles. Well, one of the problems is we don't actually know what particles. We don't have a good model for a particle. We know qualitatively what we think it'll be like. But I was feeling really bad about this until I realized recently that quantum field theory also doesn't have a good model for what particles are. In other words, if you say in
asymptotic
theory,
states in the S matrix, right? I mean,
Indeed. Right. But I mean, so if you say what actually is a proton, it's like nobody has any idea how to represent a whole proton in quantum field theory. And so what one instead does, as you were alluding to, is just say, in fact, okay, here's a piece of history I learned recently. So back in the early part of the 20th century, turns out most physicists believed that space was discrete. I didn't know
this. Is that true? I didn't know that either.
I mean, it's a very obscure thing because they didn't publish anything about it. Because what happened is, 19th century, nobody knew whether matter was discrete. Then, it became clear through Brownian motion and so on that, yes, matter is discrete. Einstein argued that light was discrete. And Einstein believed, he even has a nice letter he wrote in 1916 where he says, in the end, it will turn out that space is discrete, but we don't have the mathematical tools to analyze that yet. So I can say Einstein believed this, Bohr believed it, Heisenberg believed that space was discrete. Heisenberg tried to make a model of discrete space. None of them could make a model that was consistent with relativity. They all had kind of this lattice structures and things, and they couldn't make that consistent with relativity. They published nothing about this stuff. But what I learned recently was that in 1930 or so, Heisenberg was kind of trying to make this work. And it's like, I can't make this work. So all I'm going to do is I'm not going to even think about what happens, inside the region where particles are interacting. I'm just going to talk about the incoming states and the outgoing states. And I'm just going to put this S matrix in the middle of those. And then he never went back and thought about discrete space again. He just was describing interactions of particles in terms of what comes in and what goes out. And one thing I realized recently is sort of one of the ways to sort of understand that in quantum field theory is using Feynman diagrams and saying, there are just a very few interactions between these particles that are really going on, and we're going to draw these diagrams that represent the relationships between these different actual sort of points of interaction. What I realized recently, and should have known long ago, is that Feynman diagrams are causal graphs. They're causal diagrams. They basically tell you the causal relationship between those actual interactions of the photon and the electron interacted at this point. And the lines in the Feynman diagram are kind of telling you how that particular interaction is causally related to other interactions. So that's allowed me, and this is, again, work in progress right now, to try and reinterpret, to try and have something that's sort of underneath Feynman diagrams. It's kind of a way of going directly from the causal graphs of our models to kind of a sub-Feynman diagram. So in other words, it allows us to do something like quantum field theory in the same way that quantum field theory doesn't have to talk about particles, nor do we have to talk about particles. We can do something that is analogous to quantum field theory without having an explicit story about what the proton or the electron really is, so to speak. And what's kind of interesting is that we can make much simpler models that have sort of generate these Feynman diagram-like causal graphs. I mean, I'm reminded, I knew Dick Feynman fairly well, and one of the things he was fond of saying, because one of the things I did in particle physics early on was computing Feynman diagrams. And, I would make all these computer programs to do it and all this kind of thing. And Dick Feynman would say, this Feynman diagram idea is just a stupid idea. The fact that it takes all this effort to compute all these things, it's just the wrong way to do it. There's got to be a better way to do it. So I'm like, okay, well, what is it then? He says, well, I don't know what it is. But I think we are slowly maybe getting to something where, at least in these toy cases, I can kind of see the thing that is underneath the Feynman diagrams, and is kind of it's one of these sort of rewriting process things where you can say, well, this rewriting process, you can describe the whole rewriting process. You can break down the rewriting process into all these different possible causal graphs of the way it might have gone. And those possible causal graphs are Feynman diagrams, but the underlying rewriting process is sort of what really happened. And you can potentially analyze that in a better way than just working out all these individual Feynman diagrams.
I wonder, when you say that, it brings to mind, again, just for the audience, Feynman diagrams, you're taking a calculation and you're finding a way of breaking it up into small pieces that when you sum all of the pieces together are meant in some not mathematically rigorous way to add up to the answer to the original calculation that you were doing. But as you're saying, diagram by diagram by diagram, it is a lot of work to calculate these individual pieces. But the work of Nima, Arkani Hamad, and others on this amplitude hedron, if I'm pronouncing it correctly, was sort of a way of trying to put these guys all back together. It's like you take a vase and you shatter it, and you have to put all the pieces back together. Why shatter it at all? Maybe there's a way of dealing with it from the get-go.
Yeah.
Have you thought about that? Have you encountered?
Yeah, I'm sure that's closely related to what I'm trying to do.
Right.
In other words, I think what I have is in a sense, a much more mathematically simplistic object that I can look at, which potentially allows one to see the answer more easily. But it is, for example, in these kind of enumerating these causal graphs and things, one has a direct analog of renormalization. One of the problems of Feynman diagrams is when you actually compute them, they're full of infinities. And then you have to kind of make the argument, well, there are infinities everywhere, and all we get to notice in the world is the change in the infinity from one thing we do to another thing we do. And you get exactly the same phenomenon here, and actually the same kind of graph theoretic methods that one uses to do renormalization in Feynman diagrams seem to work in this case as well, which is kind of interesting. Another thing. But do you
see? Just because you raise it, when I teach renormalization to students, I tend to focus on the Wilsonian approach, where you have a cutoff from the get-go, and renormalization is just how the structures, the amplitudes, and the parameters change as a function of a change in the scale of the cutoff. And that way you can sort of get rid of the infinities from the get-go. And I think it's conceptually easier and probably more relevant, because many of us see quantum field theory as not relevant to arbitrarily short scales. So put a darn cutoff in there from the get-go, avoid the infinities, and now make sure that you allow your parameters to vary with a cutoff in a way that your observables don't change. Is there a version of that in the approach that you take?
Well, I don't know yet, really. I think that in terms of sort of thinking about, there's some very funky things that happen. So I'll mention a few things that I know, and this is incomplete at this point. So one thing that happens, which is kind of funky, is that you get these things in these rewrites, you get these kind of loops that can happen. So in general relativity, one always says, closed time-like curves, where you go, forwards in time, and then you can kind of go backwards in time. We don't like these. In the way that these things are set up, you effectively get lots of closed time-like curves. And there is a notion what I've been preliminarily calling subtime, which is the thing that you get if you actually are going through and enumerating. You're going through and effectively getting from this to this to this, but then you can say, well, actually, the state that we got to is exactly the same as the state that we started from. So from the point of view of an observer, those states should be conflated. So there is a subtime that goes infinitely, but observable time is only finite. And so that's the first little, that's a slightly different form of infinity than one has seen in, it's related to the infinity of virtual loops in quantum field theory. The next thing that is kind of fun is the question of when in Feynman diagrams, there's sort of one of the big features is you've got a particle and it's just going from here to there and nothing happened to it. There's this notion of the propagator, right, which is, has a mathematical formula, 1 over p squared minus m squared, or whatever it is, right?
Plus I epsilon, if you want to avoid the singularities. But anyway.
Well, yes, right. We can hopefully the approach we'll have will not even have to get into that story. But anyway, the question of what, so it seems like the particle is just going from here to there. And in the Feynman diagram, it's just like nothing happened to it. It just went from here to there. Well, actually, there's a thing that, strangely enough, is a little trick that Dick Feynman told me one day, and I don't think he ever wrote it down, but it has become known as the Feynman checkerboard, and it has a whole literature. And I didn't know until very recently that anybody knew about it other than me, so to speak. But it has to do with on a discrete lattice, you can say you just have sort of particles that kind of either go left or right, and you say that there's some, every time you look at all possible paths, and you say every time a particle was turned from left to right, there's a factor of minus I. And turns out when you add up all the possible paths, the thing you get is like the solutions to the Dirac equation. So it's like the quantum mechanical solution to what the amplitude of a particle being found at a particular position relative to its starting point is. And so effectively that's a way that you get something. It's like the beginnings of the propagator, beginnings of the thing that say what happens to a particle if it just goes from here to there. Now the thing that's kind of interesting is that the parameter that tells you the mass of the particle is how many times it got kicked, how many times the thing changed its direction. So what seems to be happening is we think about these in Feynman diagrams, we think about these causal connections between this event that is the interaction vertex, so to speak, and this other event that's another interaction vertex. And what seems to be happening is that as it's going on this, this thing which was just the free propagator, so to speak, that it is getting that you can think about it as getting continually kicked, and the amount of kicking is the mass of the particle. So what seems to happen is that from our picture, it's just this causal edge, but the causal edge that is representing, this event happened and then this other event is going to happen. The particle, insofar as it is sort of interacting with the background structure of space, in our models, it can't just go from here to there. It's going through this, it has to interact with this network. And so, in a sense, we're saying the amount of, again, this is all kind of vague at this point, but the amount of interaction of the network is the thing that tells you the mass.
And so, from this point of view, is it possible that you imagine mass emerging? I mean, if you had the right rules, the mass of the electron might be something extractable as opposed to what we normally do in quantum field theory is we just put it in from the outside.
Yeah, right. Well, so it is strange that in this picture, what's happening is that mass is associated with kind of the amount of interaction with the background structure of space, which is a little bit like the Higgs mechanism, which is kind of the standard model idea for where mass comes from, where you say, well, there's this background Higgs field everywhere, and the mass is how much the particle is interacting with that background Higgs field.
But in that case, there's a parameter, the coupling constant, which takes the place of the dial by which we can set the mass of the particle. It interacts with the Higgs field, but that coupling constant determines how much of that interaction translates into mass. Would you have a similar kind of free parameter that would play the role of lambda, the coupling constant?
Well, if we knew what particles were, the answer is no, we would not have a free parameter. In other words, if a particle was this topological structure that has this or that form, then we should be able to say, well, what is the amount of interaction that's happening with this background structure of space?
Right.
So then that would be a way of us being able to derive the masses of particles, which would be pretty cool because, as you say, that's been a thing we've never been able to do. Now, it's worth remembering that in our models, I mean, we didn't talk about this much, but there's a lot of complicated issues about observers and what you can actually what thing you extract from the structure of what's going on. And it's worth remembering that the same is true even for an electron. I mean, you say, the mass of the electron is, 0.511 MeV or whatever it is. But that is only for observers who have certain properties. It's only...
I mean, their motion relative to
energy.
But when you say observers that have certain properties, what do you mean by that in this context?
Well, I mean, so in traditional particle physics, you can think about the mass of the electron as being the amount of inertia the electron has when you kick it. But the question is, how hard did you kick it? And, depending on how hard you kick it, you will come to a different conclusion about what the mass is. And so, if you're an observer, same thing, if you're looking at the thing on a certain length scale, an observer looking at it on a very large length scale will conclude one mass, on a different length scale will conclude a different mass. So that's a kind of a way in which in traditional particle physics, you have kind of observer dependence to the so-called constants of nature, so to speak.
Right. But by that, just so I fully understand, are you talking about sort of the renormalization effects at the scale dependence of that parameter? Sure.
Yeah.
Okay.
Right.
Sure.
No, I mean, that's just an example. In traditional physics, we have more elaborate versions of the same thing.
Got it.
But I think so. In the hope would be that again, I'm sort of homing in on trying to understand kind of the underpinnings of quantum field theory, and that gives one sort of a picture of it's kind of nice that one is starting to see how things like mass can show up. I mean, to make a more general statement, because we didn't talk about this, and maybe it's worth mentioning. I mean, one of the questions is kind of, we talked about sort of how if there's some underlying rule for updating this hypergraph and so on, this and that happens. But then the question might be, well, which rule do you pick?
Yes.
Why, if you say we've got the rule for the universe, it's like the next question is, well, why did the universe get this particular rule and not another? The thing that sort of quantum mechanics is kind of tip-off about this, because in quantum mechanics we're saying there is a particular rule, but it's being applied in all possible ways. So the obvious sort of limit to that is, well, why not just apply all possible rules? And you might say, well, that's just going to make a big mess. But the thing you have to realize is that it's the same thing as with quantum mechanics. There's branching when different rules get applied, but there can be merging when those different rules lead to the same outcome. So you have this very complicated structure, which I sort of think of as the entangled limit of all possible computational processes. It's this thing I call the Ruliad, which is, and so the thing that then one has to think about is, within the Ruliad, there are observers, potentially like us, who are made from the same stuff that the Ruliad is made from, who are looking out at the Ruliad and saying, what's going on here? And they're, but because of their properties as observers, they conclude certain things about what's going on. They don't see, for example, if they were looking at something that might be a bunch of molecules bouncing around, because they are large-scale observers who are computationally bounded and so on, they don't see all those molecules bouncing around. They just say, looks like a fluid to me. And so the thing that seems to be the case is that to observers who are roughly like us, in the sense that we're computationally bounded, believe we're persistent in time, I believe that it is inevitable that those observers must conclude that second law of thermodynamics, general relativity, and quantum mechanics are the way the universe works. If the observers were different from that, and were not computationally bounded, et cetera, they might conclude completely different things about how the universe works. But the claim is that to observers like us, it is inevitable that the laws of physics have to be the way they are.
So it could be that some AI system in the future analyzes observations of the world and comes to a radically different picture of what the laws of physics are and what reality is.
There's a problem with that. We wouldn't be able to communicate with that AI system.
Right.
In other words, something which does brain-like things, which lots of systems in nature are doing computationally complicated things, but not terribly brain-like things. I mean, one feature of brains, which I've been increasingly realizing is, a lot of what we do, we've got all this sensory apparatus, we've got millions of different, bits of information that are coming in every second. But a lot of what our brain does is to try and concentrate that all down into, well, what's the next action you should take? Maybe 10 times a second or something, we're figuring out, what muscle should we move, what next action should we take. My very recent meta theory about this is when animals first emerged, it became important for the animal to know where's it going to go next. And there's only one place for it to go. It's not like the animal's going to split into 17 pieces. It's going to make a definite decision. And so the idea of a brain, which would take a lot of input data and conclude one definite thing to do next, I claim is sort of something that emerged kind of with the development of with the emergence of animals and so on. And so we're stuck with this thing that we have just one thread of experience. We don't, within a single individual, the whole of society is a different story, but within a single individual, we sort of believe that there's a single thread of experience. And that seems to be a fundamental feature of brains. And that's also one of the pieces that's necessary to see physics the way we see physics. I mean, I think it's a worthwhile sort of thought experiment to imagine that our minds worked, or brains worked, 1 million times faster than they do. So right now, I look around the room, the photons are coming to me, in a microsecond. My brain is taking milliseconds to process that. So as far as I'm concerned, it looks like there's a state of space at a particular moment in time. But if my brain worked 1 million times faster than it does, that would not be my impression. I would just be like, there's a photon from here, there's a photon from there. The fact that you aggregate them all into the structure of space is something that is particular to our scale and our kind of way of operating.
Yeah, sort of a concrete version of that, which is maybe more analogical than literal. But I have at times wasted time looking at a Necker cube and trying to see both orientations of that cube simultaneously. And the brain, at least my brain, is simply unable to do that. I don't know if anyone has had that capacity to be able to sort of experience those two things. Again, I think it's just some limitation of evolution by natural selection acting on this structure, trying to aid us in survival. And survival is a definite course of action with a definite perspective.
Yeah, no, it's an interesting example. But I think that means when you say, imagine an AI system that could sort of think about the world very differently, the answer is it's actually easy to have such a system. I mean, lots of these simple rules that I've studied, they are doing computational things just like AI systems do computational things, but they don't have a view of the world that is aligned with our view of the world.
Right.
And so it's like, yes, there's this thing. It has, we can't sort of talk to it and say, hey, let's compare our view and your view because they're just really wildly different.
Right.
But I think that the big claim is something that I absolutely do not see coming, which is the claim that the laws of physics are the way they are because we are the way we are, and it is inevitable that laws of physics will be that way. In other words, that when you say, why is general relativity true? It's like, I'm not sure, people might ask you, why is general relativity true? And I think, when I was thinking about that stuff years ago, I was like, I don't know why it's true. It's just that's what we've discovered is the way the universe works. And the big surprise here is that there's now, I think we have the beginnings of an answer to why. And it is, it is a contingent fact that we are the way we are. We might not be the way we are, but we know we are the way we are. And given that fact, we can then deduce that physics must seem to us the way it seems to us. So
and you're saying that when you say the way we are, it is simply bounded computationally and that we have a continuous experience. Again, I don't grasp all the
those
details.
seem to be the most important.
But you're saying those two criterion are enough, you think, in your structure to single out general relativity and quantum mechanics and thermodynamics as the laws. Well,
yes.
Yeah.
Yes.
Yeah.
But what I'd really like to figure out is I can't derive the 3 for the number of dimensions of space that we perceive.
Well, sometimes I like that number 3 to be 10 or 11. So, if you can get either of those numbers, I'd be perhaps even happier.
Right. No, I think that, my guess is that 3 is a consequence of some feature of the way that we are that is at some level totally obvious. But I just don't know what it is. So the fact that we parse the universe by saying space seems to be 3-dimensional doesn't have to be that way.
Sure.
We could be saying we are thinking about what's happening in space and we're just thinking about it according to this on this line. We're going through a space filling curve. We're just examining these different parts of space in that order. But no, we choose to gulp in space, so to speak, as 3 dimensions. And, there are things that I realized, like one thing I realized recently is that it's very important to our perception of physics that we are not massless.
Yeah.
Right? If we were photons, time doesn't really,
Be
time
very
doesn't
different.
progress.
I always tell my students when they ask me that, does time stop from the perspective of a photon? Is space infinitely Lorentz compressed from the perspective? I say yes, poetically, but we can't travel and no conscious being can travel at light speed. So take that with a grain of salt, for sure.
Right.
So, yeah.
Right. I mean, so it's important to us. It's another contingent fact that we are massive objects, so to speak.
Yeah.
And here's another contingent factor. Here's another thing that's interesting to perhaps. We believe in doing science that we can choose the experiments we do. It's not self-evident that will be possible. In a deterministic universe, it could be that every experiment we do, we are fated to do, so to speak. And therefore but we somehow have this belief that we can do these arbitrary experiments. We also have beliefs like the belief that we can do a controlled experiment. We can do an experiment where the thing that happens here isn't affected by the things that are happening everywhere else in the universe. I think one of the things that sometimes is confusing to people about fields other than things like physics, physics has this feature that you can do things like controlled experiments. It is the case that the simple laws tend to be the right laws and so on. The simple laws being the right laws isn't true in biology, for example. In biology, the typical experience is the most complicated possible explanation is sort of the right explanation. I mean, there's always another effect. It's I think I have some understanding actually of that now, and it's related to the whole computational reducibility story. But there are other places, like when you think about something like ethics, I think that's a place where this idea of being able to separate the thing that's happening in this particular situation from everything else that happens just doesn't work. In other words, and so some of these intuitions that we have about the physical world and things we believe about the physical world are, it's not obvious that they will be true, but they are features of the way that we deal with the physical world. And I'm kind of suspecting that somewhere in there is an assumption that we make that is totally obvious to us, but that inevitably leads us through some potentially quite circuitous route to the fact that space has to be 3-dimensional as we perceive it, for example. I mean, there are other features, like we believe in discrete objects. It's not obvious that discrete objects would be a thing. If we were fluid organisms, they wouldn't necessarily be a thing.
We wouldn't even have the conception, presumably.
Right. Right. I mean, another thing we believe in is motion. We believe that pure motion is possible. In other words, you can take a thing and move it somewhere else, and it'll still be the same thing. That's not obviously true. I mean, in other words, if space were dotted with space-time singularities, it wouldn't even be true in general relativity. But the fact that, and so, for example, one can think of particles as being essentially carriers of pure motion. Particles are things which have the feature that, the electron just moves and stays as an electron. Curiously, black holes kind of are the same kind of thing. You can take a black hole and move it around and it'll still be that same black hole. And that's maybe there's some, my guess is there is a close relationship between black holes and particles, like electrons and so on. because among other things, in our models, it's all just features of the structure of space.
Yeah, I can't help but just jumping in. I don't know if you're familiar with this paper that I wrote with Andy Strominger and Dave Morrison some years ago, but we showed, at least in certain string theoretic models, which of course you can claim we don't know that those are the right models of the world, but we had a parameter that we could continuously vary, in which a black hole mass got smaller and smaller, and then it transmuted into an elementary particle. So a direct, smooth connection between black holes and particles does exist.
In string theory.
In string theory, yeah.
That's cool.
Yeah.
I gotta look at that paper. That's
yeah.
cool.
Yeah.
I mean, it doesn't surprise me.
Sure.
But it's great anyway, so I mean, the thing for me, this whole idea that one might be able to derive physics is just completely, for me, I'd never imagined that something like that would be possible.
Yeah.
And I mean, sort of a clue, the second law of thermodynamics is kind of a clue, because it is something which for 150 years people have kind of thought might be derivable. But I don't think anybody thought that about general relativity, for example. Sure. I don't think but just to fill in, and before we have to wrap up here, but just to fill in, I've been having a lot of fun recently because a bunch of these ideas seem to be applicable to a lot of different fields. And so it's been interesting to see their application. It's been interesting to see sort of the common themes in these different areas. So one that I looked at a little while ago is metamathematics, the kind of the space of all possible mathematical theorems. And there seems to be a very sort of close analogy between, how theorems get derived from other theorems and how time progresses through the physical universe. And so, for example, one of the meta results is the idea that higher mathematics is possible. So, for example, you might say, well, we've got these very axiomatic details of mathematics, and we can, based on our definition of real numbers and this and that and the other, with a lot of effort, we can get to the point of defining what a triangle is, for example. And then with even more effort, we can get the Pythagorean theorem. But the fact is, most of the time, when you think about the Pythagorean theorem, you're not having to think down to that level of those microscopic axioms. And it's the same kind of thing, I think, as in doing fluid mechanics. A lot of the time, you can just work in terms of fluid mechanics. You don't have to dive down to the molecular dynamics level. So I think that there's sort of a non-trivial fact about mathematics, that higher level mathematics, not going down to the molecular dynamics level, is possible. And I claim that that's a thing that's very similar to the fact that we believe in things like continuum space. And I think it is another feature of being observers like us with certain computational boundedness characteristics and so on, that we can sort of think about mathematics at a higher level. And then if you really want to go sort of funky in the mathematics direction, my claim is that black holes in physical space are like decidable theories in metamathematics. So, okay, so I got to unpack that one. That one is one feature of black holes is, at least in the simplest case, is that they're a place where time stops. So that means that any path in space, you're going through this path, and it always comes to an end if you run into a black hole. So in mathematics, those paths are things like proofs. From this theorem, we derive another theorem, and so on and so on and so on. Gödel's theorem showed that there are mathematical theories, and it's in fact the generic case, where there are proofs of arbitrarily great length. There are essentially infinite paths. So when you have an undecidable theory, you have no upper bound on the length of proofs. They can just wander around through proof space, for arbitrarily long. But if you have a decidable theory, a theory where every statement that you might make can be decided by a proof of bounded length, then in effect, that isn't true anymore. So the paths always have to be finite. So it's as if time stops. So what you end up with is that what in a black hole is this physical path stopping, in metamathematics is the proof stops.
So QED is like a singularity.
Yes.
QED in the sense of at the end of the proof.
Yeah, right. And so then it gets even funkier, because in general relativity, we know that there are singularity theorems that tell one, when there's enough energy momentum, it's inevitable you'll form a singularity. Okay, so the analogous thing, not completely worked out, but the picture in metamathematics is when there's a high enough proof density, you will inevitably form a decidable theory. So when there are enough things that you can prove, you'll inevitably be able to prove everything in finite time. And so then it gets even funkier. If you say, what's the future of the physical universe? Well, there are lots of possibilities, but one thing is that you form a bunch of black holes. That when you have quantum effects, you get more than that, but roughly you form a bunch of black holes. And so then the picture is the future of physics is like the future of mathematics, because what would happen in mathematics is there inevitably would form these singularities that are decidable theories. So just as the future of the physical universe might be a bunch of black holes, the future of the mathematical universe might be the mathematical analog of black holes, namely decidable theories.
But I can't help but saying, we also know that you wait long enough and those black holes will Hawking evaporate and you'll just not have black holes and just particles wafting through space. What's the analog on the proof side?
Yeah, that's a good question. That's a good question. I mean, I think let me think. I mean, I think that I don't know. I mean, I think that I'll give you another example of a thing that you can see on the sort of the two sides. In physical space, one of the notable facts is that space is somewhat homogeneous, and things like motion is possible. Space is sort of the same here and there. You can move things around. They're sort of the same. In mathematics, different places in mathematical space are like different kinds of mathematical theories, like an algebraic way to represent things, or a geometrical way to represent things, or a category theory way to represent things or something. And one of the things that's been found in modern mathematics is these remarkable dualities between different areas of mathematics, where you can rewrite them, in terms of other, in a different sort of mathematical language. So the claim would be that the homogeneity of physical space is analogous to a homogeneity in mathematical space, and that the possibility of motion in physical space is like the possibility of making these dualities, these translations between different mathematical areas. So that's an example of another correspondence. I mean, the question about quantum mechanics is an interesting one in mathematics. Let me give you a little bit of an indication of something. I don't know really how this works,
Sure.
So in mathematics, you're often asking the question, can I get a proof of this thing? So a proof is a path from one set of theorems to another set of theorems. It's a way of going from this theorem, prove the next one, so on, get to the one you want. Okay, so people say in mathematics, I want to see a proof of that thing. So it's saying, I want to find a path. But actually, there may be many paths. There may be many proofs. There will be, in general, many proofs of the same thing. So in a sense, the analog of sort of quantum mechanics is that there are many proofs of the same thing. So then the question would be, what can you say about the space of possible proofs of the same thing? And that's a thing which people have sort of slightly started studying in homotopy type theory and so on, or they didn't really get very far. The topology of proof space is something rather interesting and rather unstudied. There is an analogy to that in studying games. For example, let's say tic-tac-toe. You've got the state of the board for tic-tac-toe. You make a move. You turn it into another state of the board. You can make this game graph of all the possible moves you can make in tic-tac-toe. And you can ask, what is the structure of that graph? And you can ask, does that graph, for example, have sort of continuous deformation from one path, one possible sequence of moves in the game to another sequence of moves? So, for example, one case I know is the Towers of Hanoi puzzle, where you're putting these disks, stacking these disks up. If you make the game graph of the Towers of Hanoi puzzle, it is a fractal Sierpinski kind of structure. So it has a great big hole in the middle. So in other words, you make a commitment. You're either doing it this way or you're doing it that way. And that's analogous to sort of, you can think of that like a proof space. And so I think, my initial sort of take would be that the story of quantum mechanics in mathematical space is related to a story of kind of thinking about the multiple possible proofs that you can make of a particular statement. And, we don't have a good intuition about that. I mean, I think, that's just not a thing, because in mathematics, it's just like, I just want a proof. Give me any proof. This whole thing about, and I think it's also related to our fundamental sort of single thread of experience. We're very bad at thinking about these kind of multiple paths of things happening. It's a thing that's afflicted sort of distributed computing, where you have many computers working on some problem. And it's like, well, they could all be doing it, and they're all sort of doing it in parallel, and we don't know how they sort of merge with each other. And that's a thing we just find it hard to think about.
Sure. One of the quick things, even before we wrap up, is so fascinating. But we spoke about black holes, the center point being like the end of time. The Big Bang, we can also perhaps think of as the beginning of time. Your approach, does it say anything about the beginning? Does it give us a way of thinking about it?
Yeah. No, so I think one of the things that is, the general picture would be the beginning of the universe. It's probably infinite dimensional. And it probably, you have some little tiny network, and it's effectively everything is connected to everything else. And gradually, as the thing expands, you can kind of start thinking that things are less connected. And so the thing is sort of cooling down to being, well, we don't know why it's 3, but, a finite dimensional universe. Now, what implication does that have? Well, it means you don't have to worry about inflation, all these other kinds of things, because you know why the fact that if the universe was infinite dimensional initially, it's, everything is kind of causally connected to everything else. You don't have to explain why one part of the universe is similar to another part of the universe, even though it hadn't sort of had a chance to see that other part of the universe during the actual evolution of the universe. So for me, this is
I see.
I mean,
so the horizon problem, you say you solve from the get-go because causal connections are almost part of the initial state in that way of thinking about it.
Yes, that would be the idea. I mean, I think that, it's ironic because you may know I wrote this paper with Rocky Cole back in, when was it? 1978, 1979, where we were looking at the expansion rate of the early universe. And we realized that, there could be an exponential phase of the expansion of the universe. And we realized that would have, all these consequences.
Wait, so you were there, you were at inflation before inflation? I didn't know that.
Yes.
Wow.
Yeah. No, but okay, this is one of these sort of stories about doing science that's sort of interesting, which was, so I worked out, in order to get any significant effect that one would care about, the universe would have to supercool by 10 orders of magnitude. And I was like, I was looking at, nucleation in liquids and all this kind of thing. And I'm like, this is not going to happen. The universe is not homogeneous enough for that to be a thing. So it's like we relegated to a footnote this statement about, what happens if you get this period of exponential expansion, et cetera, et cetera, et cetera. And what's sort of, to me, interesting about that is if it was sort of the fact that when people really, trotted out inflation, what was happening there was people said the result is so worthwhile that even though it requires a slightly, implausible assumption, it's worth making the implausible assumption because the payoff is so big. And I think that was for me, that was an interesting kind of realization about kind of the metastructure of science, that's a reasonable thing to do.
Yeah.
To say but anyway, so
but just one thing on that's interesting to say, because Andre Linde also found inflation in the mid 70s, but couldn't solve the so-called graceful exit problem, and didn't think that the payoff was large enough, worthwhile enough to write a paper on it. And he basically put it in his desk drawer and only revisited after Alan Guth wrote his paper. And Linde was like, oh my God, it's out there in the world and people are taking it seriously. Now he went back at it with a vengeance. So. Right.
No, I think I remember Linde's work, I think he worked on related things actually around the same time. So yes, it was one of those things where the most significant thing was deciding that it was as significant as it was and taking it that seriously, so to speak.
Exactly.
Now, it may turn out that it's all nonsense anyway, but that's which is, so, that would make me feel better about my footnote, so to speak.
Right.
But I think it's still, kind of that's sort of the picture of the early universe. And I think one of the things that I would love to be able to do is to work that out in enough detail to be able to see things like, would I expect that dimension fluctuations would survive past, the time of recombination where the universe became transparent? And will we be able to, could we see kind of inhomogeneities in the cosmic microwave background or something that could be associated with dimension fluctuations?
Right.
I mean, just to add another little curveball to the whole story, in general relativity, we usually think of things in terms of, well, we've got 3 plus 1 dimensional space, and then we have curvature of 3 plus 1 dimensional space. But actually, the mathematics is rather similar, at least for small gravitational fields, to saying we have we have zero curvature, but we have deviations in the dimensional
Number
space.
of dimensions. I see.
Because if you just think about the volume
Actually,
of
no, I
geodesic
can picture
ball,
that. Sure, of course.
Right.
Yeah.
And so
makes sense.
that throws yet another curveball into the whole thing.
Right.
So I don't know, for example, one of the things I looked at a little bit was dimension waves, which are the analog of gravitational waves for dimension fluctuations.
Sure.
Again, I don't know how they work, and but those are, the thing. I mean, I would say that one of the issues is we have to rebuild. Basically, we're sort of rewinding a bunch of mathematical science all the way back to Euclid. So it's kind of a heavy lift to get from Euclid to where we are today with a different set of assumptions. However, we have at least one really big advantage, which is we can simulate stuff on computers.
Sure.
And that means that we can get an idea, which is sort of the, for me, the kind of meta approach that I've taken. You simulate things on a computer, it does a lot of stuff you don't expect. Then you try and figure out what the big picture is, which is almost sort of a philosophical activity. And it's kind of this, you've got kind of the computer experiments, you've got the philosophy, and somehow in the middle, you hope to get some sort of, results about science. And as an added bonus, every so often you can throw in some fancy mathematical physics to help you see, how those things connect.
Yeah, one final counterfactual that I can't resist asking. So you mentioned the footnote in the paper, Rocky Cove, and you wrote, just wondering, if that hadn't been just a footnote, but it had really been a description of an inflation-like theory, and it took the physics world by storm, the way Alan Gouth's paper did in 1980, just a couple years later, do you imagine your career would have gone in a radically different trajectory, or would it somehow have found its way to pretty much what you do now?
That's an interesting question. I mean, look, I was a pretty successful young particle physics operative.
Yeah.
And it's kind of cool because I was involved in a field that was sort of the hot field of its time when I was a kind of a late teenager. And so, I had the...
Wait, you're doing particle physics as a teenager?
Yeah, I wrote my first paper when I was 15.
15?
Yeah.
So what age were you in graduate school?
I got my PhD when I was 20.
Oh, so you finished at 20?
Yeah.
Wow.
No, I wrote a bunch of stuff about QCD and about cosmology when I was 17, 18 years old.
I see.
That have been, I'm happy to say, seem to have been surviving papers and things. People still care about them. And that stuff with Rocky, I was probably 18, 19 years old or something. It was, I think I was a decently successful operative in that area. I think I kind of got interested in more and more foundational things, and also particle physics, frankly, kind of, it kind of went into cruise mode to a large extent. And my last papers in particle physics were like 1982 or something like this, which was, and I think in another piece of sort of the history of this whole thing, I was, a faculty person at Caltech. And when I was, 21, 22 years old, whatever, and the other thing that happened was I developed this big computer system. And in those days, being a professor and doing things like starting companies, they were not compatible activities. And so that ended up with me kind of having this sort of big flap with Caltech. And so I quit.
I see. I didn't know that.
And had that not happened, I
Wow.
might still be, professoring, so to speak. That was kind of, I then went to the Institute for Advanced Study in Princeton, which had the feature that its then director said, actually its then chairman of its board said, we gave away the computer when von Neumann kind of died. So, all this intellectual property stuff, we're just not worried about that.
I see.
I don't know whether they've changed their point of view.
Perfect. Yeah, I'm sure they did.
So that was a convenient feature at the time. But anyway, so no, I mean, the fact is that certainly in terms of, I might have stayed, being a physics professor type thing. I'm not sure that I would have been a perfect fit, because I think I'm a bit, I know that I'm, my life kind of leading companies and things like that has the feature that companies are a very efficient machine for turning ideas that you have into real things. And I think academia, for me at least, was not as efficient. And I think I would have kind of found the path of least action or something in somewhere along the way. But it's certainly I also, if you ask, the things I've done recently in fundamental physics, would I have gotten there if I'd gone, still been doing physics, done inflation and done more? The answer to that, I think, is absolutely definitively no.
Right, because you wouldn't have had the free, yeah.
I mean, without question, because the fact is that, as I think about the physics project, which I think is, it seems to have gone really well, I say, what was necessary for that project to happen? And the answer is a whole series of things, like the fact that I, used to do kind of, standard particle physics and cosmology. So I know that stuff pretty well. That was a necessary feature. The fact that I built a bunch of tools that let one explore the kinds of things that I wanted to explore, and the fact that I got a bunch of intuition from looking at experiments that I looked at for quite different reasons. And, the whole series of these things that ended up being sort of, you have to have that whole stack to get there. And I think, in other words, to me, I see the things we're trying to do as being sort of a different paradigmatic direction for things like physics. And, it's kind of like to break out of the 100-year tradition of the particular way of doing physics that comes from mathematical physics and so on, is you kind of have to, you have to have seen the outside, so to speak. I think another feature is you have to not care that much, because in other words, in some sense, the fact that our physics project has worked as well as it has is really cool. I'm really excited about it, but it was not what I was expecting to be doing at this point in my life, so to speak. It was, it was just sort of a bonus feature that was possible because, I'd built a bunch of other things. And then I kind of decided, what the heck, I might as well try doing this, because I've been meaning to try for 30 years. And I would, like, a couple of young physicists sort of said, you got to do this. So I'm like, okay, fine, let's see whether this actually works. And then it went a lot better than I expected it to go.
Wow. Well, Stephen, it's always a pleasure speaking with you, and I hope we can do it again at some point in the not-too-distant future, but thanks so much for spending the time today.
Yeah, happy to.